think
Okay.
that's 30 minutes. So.
Yeah. Yeah, no,
Oh yeah, I'll play YouTube.
I'm fine with it. No, I'm going to get a nice, big, fancy video thing for my project in the fall, so at some point I'll have a better camera. So, all right, hey, it's good to see all of you guys. Hope that the weekend is going well. Obviously, we still have a few days before we have our exam coming up, but I appreciate you stopping by to go through this review with me. You know, the material that's going to be covered on this test, it all kind of ties together, right? You know, we start off with Chapter 7. Chapter 7 is about the Euler phi function. We brought that up as a kind of a natural generalization of Fermat's little theorem, so that you could take high powers of a number modulo any natural number n, not just a prime number. So, so that was where we sort of started from, and of course Euler's theorem uses the Euler phi function. So you're going to want to be familiar with the Euler phi function, know how to calculate it for any given number. You're going to want to be able to use it in applications of Euler's theorem, for example. You're going to want to be able to do some of the types of proofs that are in the group work, and I'm going to do another example today of proving like what values can come out of that Euler phi function. So for example, we know that as long as n is at least 3, the Euler phi function is always even. Okay, so these are things that can be proved, and one of the nice things I like about those kinds of problems is that to do that kind of, for example, to prove that phi of n can never be equal to n over 4, I think that was one of the group work problems. You use the fundamental theorem of arithmetic as part of the solution to that. So I'm always looking for problems that combine different things together. And that's why I said that this section of material really does blend a lot of things together. I mean, after Euler's theorem and after we studied the Euler phi function, we went into primitive roots and talked about primitive roots. Primitive roots are very closely related to quadratic residues and non-residues, which was the chapter after that. And all of it has to do with orders of elements. Orders of elements is something that is sort of fundamental now. The smallest power of an element that's congruent to 1 modulo n is the order of that element. So all these things are kind of closely linked together. And then we had a nice application in the field of cryptography. So there's a little bit of that in there too. It's very computational. So so there's a fair bit of theory. There's a fair bit of computation. You should be expecting some of both. I have a lot of good examples of both here today. I won't ask you any question on this exam that I could have asked you on the last exam. So there won't be anything that is solely dependent on material from midterm number 1. But that's not to say that you don't need to know anything from before the first test. Because, for example, the fundamental theorem of arithmetic is used in proving properties of the Euler phi function in the example I just gave you. Another example of something from earlier material that I won't directly ask you about, but that you need to know, would be the Chinese remainder theorem. Right? You're going to need to know that theorem. What if I ask you to solve a congruence modulo p times q? Right? Well, a good strategy would be to solve it modulo p and solve it modulo q, right? And so, and then use the CRT to put them together. So, although I'm not going to ask you anything that I could have asked you before, please don't forget about like some of that earlier material. You are going to need some of it from time to time. So I have just a whole bunch of practice problems. I really like these problems. So we're going to try and go through some of them. Maybe we'll get through all of them. We'll just see how it goes. And then also don't forget, you have homework that I think a few people have turned it in. There's homework that I'm asking you to turn in by tonight. And I will post the solutions by tonight. At that point, everything is going to be up. I put up a practice quiz for this most recent week. I've just done that last night. So there's a practice quiz pretty much for every single week since the last test. And we're going to we have group works, basically 5 group, we've done 4 groups works, we're going to do another one on Monday. That all of that stuff is posted as well. So it's all up there. And so you should take a look at it. There's a sample test. I looked back at that sample test and thought, wow, I wrote a good test last time I taught the class. I really like it, so you should definitely sit down and take it. You can use a calculator. I think we made this agreement. You can bring a calculator. Do not bring your iPhone as your calculator, however. Okay, so bring some other calculator. I just have a little TI-83 here, just to do basic calculations. It's not going to help you with the theoretical problems, but it might speed up the some of the calculation problems as we're going along. So, all right, so that's kind of where I see things. Why don't we just dive on in? I'm going to just mix this up a little bit, kind of jump around from one thing to the next. So let's do some practice problems. And again, just like the review that we did before the first test, this is very, very open-ended. You know, I'm happy to elaborate. So please fire out your questions if you have them. You know, if we end up staying past 6, it's fine with me. If you have to leave at any time, that's fine too. So it's very, very casual, very casual. So, okay, let's start with something fairly gentle here, I hope, which is the following problem. Let's solve the congruence x squared is congruent to 11 mod 35 if possible. Okay, so let's see if we can solve that. Can anybody tell me where this fits into the material? What topic? Quadratic residues, what did you say? Same thing, quadratic residues. Yeah, exactly. You're solving a quadratic congruence, right? You're solving a quadratic congruence, and so can we just go straight into the theory of quadratic congruences that we've just been learning in chapter 9? What's the problem? 35 is not a prime, right? So this is actually just what I was just talking about a minute ago. You see a problem like this, really the strategy is going to be to solve it mod 5 and solve it mod 7, and then use the CRT to glue the solutions together. So anything that is a solution to this quadratic congruence must also be a solution mod 5 and mod 7. So we can break this down into x squared congruent to 11 mod 5 and x squared congruent to 11 mod 7, and we can solve both of these separately. Now remember that when you have congruences modulo a prime, when you have polynomial congruences modulo a prime, the number of solutions. What can you tell me about the number of solutions? Chris?
There's only one unit modulo. There's only one increment solution.
No. Lisa?
There's either 0 or 2.
No. Well, in this case, yes, but in general, that's not the theorem. That's not the theorem we're looking for. What theorem do we have that talks about how many solutions we can have to a polynomial congruence? Let's say the polynomial has degree n. It's a polynomial congruence modulo a prime. Thank you. At most n solutions, right? So that in this case, this is a quadratic congruence, so there's at most 2 solutions. Guys, it's possible to have 0 solutions, 1 solution, or 2 solutions to these. Okay, so any of those are possible. But my point is, if we find 2 solutions to either one of these, we can then stop. Okay. Now, the nice thing about reducing these moduli is that when you get down to small primes, it's pretty easy to just figure it out sort of by inspection. For example, in the world of mod 5, what would you do with 11? Change it to 1, right? And now you're just looking for solutions to x squared congruent to 1 mod 5, right? So in other words, this is congruent to 1 mod 5, and I think everybody could solve that one very fast. What are the 2 solutions to x squared congruent to 1 in mod 5? Plus and minus 1. Very good. Okay, so x is congruent to plus or minus 1 mod 5. And on this side, what would you do with 11 in mod 7? Change it to 4, exactly. It's equivalent to 4, congruent to 4 in mod 7. So can somebody tell me the solutions to this one? Plus and minus 2, very good. So we actually have 2 solutions to each of those, right? 2 solutions to each of those. And any solution, any values of x that solve both of these will then be a solution to the original congruence. Okay? So in other words, if x squared is congruent to 11 mod 5 and mod 7, then they will be congruent to 11 mod 35. If 5 divides something and 7 divides something, then so does 35. Just going back to the earlier material. Okay, so basically what you have to do now is put together 4 combinations of options here. So you can have x congruent to 1 mod 5 and congruent to 2 mod 7. So x congruent to, so this would be like case 1. X is congruent to 1 mod 5 and x is congruent to 2 mod 7. Now if it's something that small, like that, you could probably figure this one out without using the Chinese remainder theorem and going through the whole process. So if you want to just come up with a solution by trial and error, I would be okay with that. For example, you could just start looking at the second congruent since it's got the bigger modulus. I'd probably do that. And just start with 2 and keep adding 7. And in each case, test it up against the first one. So for example, you're going to quickly find that 16, x equals 16 works in the second congruence and in the first congruence, just by inspection. Okay, so x would be congruent to 16, and that's a unique solution, by the Chinese remainder theorem, that is a unique solution modulo 35. Okay, so that is going to be one of your 4 solutions to the to this problem. Okay, does everybody see how I did that? Just by inspection. Okay, and then case 2 would be x congruent to 1 mod 5 and x congruent to negative 2 mod 7. And again, it's very fast to check that the solution to this is going to be x congruent to 26 mod 35. Okay? You just see that by inspection. Of course, if you can't do it by inspection, you're always welcome to just apply the Chinese remainder theorem to it, but it's not necessary here, right? Okay, and then there's going to be 2 more cases. Maybe I can just skip those. Kind of good. You see what I'm doing? I'm pairing up one of these with one of these, and there's 4 ways to do that. Okay? So cases 3 and 4 are similar. I think I'll just leave that off for now. Okay. So everybody all right with that? Everybody comfortable with that? Okay. If so, we can go on. And notice here we're actually asking to find the solution. So this stuff we've been doing in chapter 9 with quadratic reciprocity and the Legendre symbol and so on, where it's either +1 or -1, that's just simply a thumbs up or thumbs down whether there, is there a solution or is there not a solution. But it doesn't really help you to find the solution. It's actually something I wanted to talk about. Let me see if I can, well, I'll do a couple examples and then we'll talk about that. Like, how do you actually find the solutions? So here we did it by sort of brute force, reducing the moduli and just looking at a system of 2 equations, and we were able to figure it out. But in general, that's a good thing to be thinking about. I mean, if we're talking about quadratic congruences and we say, yes, there's a solution, wouldn't we want to know what the solution is? You wouldn't just want to know, yep, there's a solution. I mean, I guess you could just stop there, but generally you want to know more than that. Okay. All right, so let's go on. That's all I had to say about that problem. Everybody good so far? Not bad. Yeah, Lisa?
So there ends up being
4
4
solutions.
solutions,
Yep.
even though we're solving for x squared. Oh, we're finding out what the quadratic residues of that equal 11. Is what we're doing?
Yeah. These are basically the quadratic residues of 11. point is that there are, okay, so that brings up another question. This is a quadratic congruence, but I'm going to get 4 solutions. Is there a problem with that? Why is there not a problem with that? Right, as soon as your modulus is not a prime, you are not restricted to having less solutions than the degree of the polynomial. So yeah, so you're going to get 4 solutions here. I can tell you what the other 2 are if you want to know.
It's just negative 26 and negative 16.
Yeah. Yeah, of course. That's true. Yeah, once you find these 2, then the additional solutions because it's x squared congruent to 11, you're going to get x congruent to minus 16 and x congruent to minus 9.
No, minus 16 and minus 26. Right?
Yeah, sorry, minus 16 and minus 26.
Yeah.
Yeah, right. Mod 35, exactly. There we go. Okay. Okay, so let's try another problem here. I want to practice this Legendre symbol stuff a little bit. Okay, so let's compute, there's going to be a couple of parts here. Let's compute the Legendre symbol of 14 in modulo 137. Okay. So you have to know your properties of the Legendre symbol. You have to know when you can apply the quadratic reciprocity law, which is the one that allows you to flip the symbol over. Remember, you can't flip it over unless both the top and the bottom are prime, odd primes actually. So I'm not ready to apply the quadratic reciprocity law here. Okay, so what could I apply, or what could I do? Say again, Fran? Okay, the multiplicative property just tells me what?
You get 7 over 137 times 2 over 137.
Okay, so you get the Legendre symbol of 7 and 2 in mod 137. Okay, and then, can I flip this one over? No, so anytime you have a 2 on top, anytime you have 2 on top, we have a formula for it, right? Okay, so let's remember what that is. That's probably worth recalling here. Do people remember? I haven't proved this yet. I'm going to prove it on Monday. But do you remember what the formula is? It's either 1 or negative 1 according to what?
It's the modulo 8.
This is a mod 8 condition on the prime p. So if p is congruent to 1 or negative 1 mod 8, then it's positive 1. And if p is congruent to, I think, 3 or negative 3 mod 8, then it's negative 1. I think I used 1 and 7 here and 3 and 5 here, but it's the same thing. That's what I've written there now. Okay, so these are your choices. So you just have to look at 137 and figure out in mod 8 what it's congruent to. It's obviously congruent to some odd number. So does anybody know?
1.
It's congruent to 1. So 136 is divisible by 8. Do I believe that? Yeah, I do believe that. Okay, so therefore 130, said to do it in my head right. Okay, so this is equal to, this is congruent to 1 mod 8, so we're in the first case, so we can just get rid of it. It's congruent to 1 and we just reduce to that. Okay, now what would you have me do? This is 2 odd primes, right? So you can flip this over. Now remember, there's only one situation when you have to change the sign. Most of the time you get to flip it over for free. The only time when you have to put a minus sign in there is if both of these primes are congruent to 3 mod 4. Is that the case here? No, because 137, right, in the world of mod 4 is congruent to 1. So if either one of these 2 numbers is congruent to 1 mod 4, then you just flip over with no change. So this flips over to the Legendre symbol of 137 in mod 7. And what is the purpose of flipping it over? Why does that make your life better? Because you can reduce 137 in mod 7. Okay, so when we reduce 137 in mod 7, what do we get?
4.
Yeah, it's 4 actually. So it's 133 is a multiple of 7. So it's just 4. And what's the Legendre symbol of 4 in mod 7?
1.
It's a perfect square. 4 is a perfect square in any modulus, so it's just going to be 1. Okay, so that is equal to 1, right? Okay, so that begs the question. So that tells us that, so what is that really telling us? That's telling us that x squared congruent to 14 mod 137. If I look at that congruence, it has a solution, right? Plus 1 means it has a solution. Has a solution. So now I want to get back to what I was saying a moment ago. How do you find the solution? How would you go about finding this solution if you were pressed to do that? Anybody have any suggestions for me on that? Say again? That's it. Yeah, use the theory of indices. Okay, so use the theory of indices. So here's something else that I'm going to give you on the test. I guess I didn't put this in the review packet, but I'm going to give this to you. I'm going to give you this table 1 in the back of the book. This is the table that tells you the least primitive root of every single prime number up to 1,000. Okay, so 137 is a prime number that's less than 1,000, and in this book it tells you that the smallest primitive root of 137 is 3. So you'll know that fact. So 3 is a primitive root. So to solve this, of course, to use the theory of indices, you have to have a primitive root. So I'm not going to be asking you to, like, you need to find an element whose order is phi of 137, which would be 136. So that becomes quite a chore to figure out, well, I need an element of order 136. So instead of having to do that, I can just hand you a primitive root in the form of that table and let you work with it. So let's use r equals 3. This is a primitive root of 137. And then, yeah, you would solve this by using indices. So you would take this equation, and we have our properties of indices. So remember that it acts like a logarithm. Basically, the properties are like logs. So I'm just going to say here, take index using this value of r. So you're going to get 2 times the index of x relative to the primitive root 3. So indice with respect to 3 of x is congruent to the index of 14 relative to 3. And this would be modulo what? 136, exactly right. Okay. And so what you would hopefully do is you would solve for this. Okay, so you would have to know the index of 14. So you'd have to know what power of 3. We're not going to do this right now. Or you'd have to figure out, you'll be given a table, which when you look at the sample test, you'll see that's sort of how I like to set up these problems. So I give you a table, and you would look in the table to see, well, what is this number congruent to? Okay. Because it's not clear. Basically, you're trying to solve 3 to the a power congruent to 14 mod 137. That's how you decide what the index of 3 is. So you have to start taking powers of 3. And it could be anything, it could be any value between 1 and 136. This is going to be a painfully large table. So I'm not going to worry about it right now because I didn't work it out ahead of time. But that's what you would do. You would solve for this value of a from the table, and then you would know what the index, well, then you'd have a value to put right here. And now you've got 2 times something congruent to something mod 136, and you're going to want to divide the congruence through by 2 everywhere, as we did in the first part of the semester. And then you'll know what the index of x is. And then you can use the table again to figure out what x is. Right? So that's basically how you do it. Yeah. Okay. And when you divide, let me just make one more comment here. When you divide the congruence through by 2, you're going to be talking about a congruence that is in the world of mod 68. 68 is half of 136, right? So you're going to be getting a value for the index of x in mod 68, which means in this mod, there will actually be two solutions, right? Let's say let's say that this index comes out to 10 in mod 68. Just making up a number. Well, then your solutions are 10 and 78. And so then you look in the table and you find two values. You should be expecting two values of x. Of course, you can just take one of them and then put a minus sign in front of it to get the other, because you know based on the form of this congruence that as soon as you have one solution to it, its negative or opposite will also be a solution. Okay, so remember, the only way you'll get one solution is if this was a 0, in which case x is 0. Otherwise, all quadratic congruences modulo a prime are going to have either 0 or 2 solutions. And once you've shown that there is at least one solution, it has a solution, well, there's going to be 2. Okay, so that's just my point. I just wanted to point out that we've been doing a lot of problems where we come up with the Legendre symbol, either 1 or -1, but why would you stop there? You might want to actually solve the congruence, and using indices would be a good way to do that. Yeah.
So, in the example that you were saying, so 10 would be equal to the indices 3x, right? Not the x.
Right. It'd be the index.
The index.
So that would be the value on the second. So if you drew your table, this is the way I usually draw these tables. You put x here and the index there, right? So if I, for example, decided that 10 was the solution, I'm just making that up, then I would get a value of x right here, and then over here somewhere you'd have 78, and that would be another solution to this congruence, and there'd be another number here. What I'm telling you, though, is that these two numbers will be negatives of each other in the world of mod 137. They have to be. Yeah. Does that make sense? Okay. Okay, great. Okay, so that's good. Let's see here. All right, let me give you another, maybe something a little more theoretical. Again, I'll try to tie some different things together here a little bit. All right, so here's number B. Well, I only did part A. Yeah, sorry, I'm not quite ready for anything more theoretical there. Let me do part. Let me do part B here first of all. So let's do the Legendre symbol of 101 in mod 1987. Let's just practice this one more time, and then we'll get into the slightly more theoretical thing. Okay, so these are both going to be primes. You have to trust me on that. If the thing on the bottom is not a prime, I should never see the thing on the bottom of the Legendre symbol be it not a prime. It has to be a prime. Okay, so you have to trust me these are both primes. So what would you be wanting to do right now? Flip this thing over, and can I do it without a minus sign, or do I need a minus sign? I don't need a minus sign, and I don't need to figure out 1987 for that. I can just look at 101. In mod 4, it's congruent to 1, right? If either of these numbers is congruent to 1 in mod 4, I can flip it over with no change. So this is 1987, the Legendre symbol of that in mod 101. Okay, great. And now I'm going to do what with this? Reduce 1987. Well, 101 is a fairly nice number to work with. If I multiply it by 19, I'll get 1919. This is why you're going to have a calculator if you want it. I'm trying to do this in my head right now. I got a good night's sleep last night just so I could be sure I could do some of these calculations. Okay, so 1919 is the same as 0 in mod 101. So 1987 in the world of mod 101, I just need to subtract 1919 from it, and I think I'm going to get 68. No? Am I wrong? Okay, I hope I'm right. 68. I can check my notes, I guess. Yeah, 68. See? Okay, good. So what do I do with 68 now? Do I flip it over again? Please don't. 68 is not prime. I can't do that. But what can I do? Yeah, I want to look at, okay, if it's not a prime, then it's going to have a nice factorization.